Hello everyone, welcome back to my YouTube channel. In this video, I want to continue to solve Physics EJU 2018 second session for the last 4 questions. You can check list on the description box below if you want to watch the solution for the previous number, or check my EJU playlist if you want to watch the solution for the other paper. Okay, let's start from number 16 and then I will continue to explain until the last number, which is number 19. For number 16, as shown in the figure below, we have 3 straight sufficiently long conducting wires are parallel to one another and perpendicular to this page, passing through the vertices of equilateral triangle ABC within this page. So basically, we have 3 conducting parallel wires, and then they are located at the vertex of equilateral triangle. Electric current of the same magnitude I flow through the 3 wires, all in the direction from back of this page to the front. So all the wire has a current with same magnitude and flow in the same direction. Let us denote FB and FC. The forces exerted on the segment of length L of the wire passing through A by the current flowing through B and by the current flowing through C. Let us denote as F the resultant force of FB and FC. So, FB and FC basically a force that is produced due to wire B and wire C on wire A. And then F is the resultant force of FB and FC. What is the direction of F? This is our first question in terms of the direction indicated by the arrow A until D in the figure. A, B, C, D. And then what is the ratio F to FB, where F is the magnitude of F? They already tells us that F is the resultant force of FB and FC, and FB denotes the magnitude of FB. To answer this question, you need to know one concept, which is if you have a parallel straight wire and then on that wire a current flows, then in the wire there is a magnetic force. So basically, if I have 2 straight wire like this, and then in this wire there is a current flow, let's say the direction of the current is in the same direction. The direction can go up like this, can also going down like this. It doesn't matter. Basically, if the direction of the current is in the same direction, then there will be a magnetic force acting on each wire. The direction of the magnetic force acting on each wire, in the case the 2 currents are in the same direction, is attract to each other. So the direction of the magnetic force acting on each wire is attract to each other. If the direction of the current is opposite, then the force or the magnetic force will repel to each other. So let's say I have 2 straight wire like this, and then the direction of the current, one is going up and then the other one is going down like this. There will be a magnetic force acting on each wire, and the direction of the magnetic force will repel to each other. Something like this. I do not explain the concept behind this. I think you should try by yourself to find out why the direction of the magnetic force in the first case is attract to each other, and then in the second case they will repel each other. But to answer this question we need this concept. Okay, since the direction of wire in A, B and C, the direction of the current in the wire A, B and C are all in the same direction, so they will an attractive force between A and B and A with C. So if I draw the force acting on A, since we focus on A, if I draw a force acting on A, the direction of magnetic force acting on A due to B is attract each other like this. On wire B, there also a magnetic force attracted to A, but we do not focus on this. We just focus on A. This is FB, and then there is also magnetic force acting on A due to C. Since the direction of the current is the same, then the direction of force will attract each other. If I draw in the same diagram, this is FC. FC. The magnitude of this attractive force or this repulsion force is depend on the current on both wires and the distance between the wires. Since the current in A, B and also C are the same, and the distance from A to B and A to C are the same, I can conclude that FB must equals to FC. FB must equals to FC. I will write it down. FB equals to FC. I talk about its magnitude, yeah. So the magnitude of FB is equals to the magnitude of FC. And then I want to find the direction of F, which is the resultant force of FB and FC. As you can see from this diagram, since FB is equals to FC, if you resolve FB into horizontal direction and FC into horizontal direction, these two forces will cancel out. And then if you resolve FB to the vertical direction and you resolve FC to the vertical direction, they will adding up, since it is pointed the same direction. So the direction of F is toward C. One from FB like this, and then the other one from FC like this. So the direction of force toward point C, or the direction of F indicated in the arrow C. So my answer is either number 5 or number 6. And then I want to find the ratio of F to FB. Since FC equals to FB, I can write it down as FB. And then if we want to find the resultant or the magnitude of the resultant force between two forces like this, we can use the equation. The magnitude of resultant force is equals to square root FB square plus FC square plus 2 times FB FC cos angle between those two forces. This is the formula that we can use if we want to find the magnitude of the two forces, which is makes an angle alpha. This is the resultant or the magnitude of the resultant force. Since FB is equals to FC, I can write down FC as FB. So I will get square root FB square plus FB square plus 2 times FB times FB times cos alpha. As you know, since we have equilateral triangle, then alpha is equals to 60 degree. Cos 60 degree is equals to half times half. You can cancel out 2 and half here, and then you will obtain square root FB square plus FB square plus FB squared, which is 3FB squared. Therefore, the magnitude of the resultant force F is equals to square root of 3FB. That means, if I want to find the ratio F and FB, we can say that F over FB is equals to square root of 3. So my final answer for question number 16 is option 6. The direction is toward or indicated by the arrow C, and then the ratio F to FB is equals to square root of 3. This is for question number 16. I will proceed to question number 17. As shown in the figure below, a uniform magnetic field. We have a uniform magnetic field. Magnitude of the magnetic flux density is B. Is applied to a sufficiently wide region of an XY plane, which is this page, perpendicular to this page and in the direction from the back of the page to the front, as you can see in this diagram. I have a magnetic field applied in this whole page. The direction is from the back of the page to the front of the page. So the direction is dot like this. A represents a charged particle with mass m that has a negative quantity of electric field, which is negative Q, where Q greater than 0. This is A. So A is a negatively charged particle with mass m, and the charge is negative Q. At time t equals to 0, at initial, A is launched from origin O in the positive direction of the y-axis with an initial speed VO, as you can see in this diagram. The initial speed of A is VO, the direction is positive y-axis. Let us denote x1, the coordinate of the point where A returned to the x-axis for the first time, as t1 the time of that occurrence. So x1 is the point where A returned to the x-axis for the first time, and then t1 is the time taken for the particle to return to the x-axis at the first time. We want to find x1 and t1. From the table or from 1 until 8 below, choose the correct combination. To answer this question, you need to know that if we have a charged particle, if I have a charged particle, let's say the charged particle is positive, move in the magnetic field, move, that means it has an initial speed or it has a speed in the magnetic field. So this is the region of magnetic field. This particle will experience a magnetic force. This particle will experience a magnetic force. To determine the direction of the magnetic force, we can use Fleming left hand rule. Let me tell you the diagram for Fleming left hand rule. By using your left hand, this is the position of your finger, you can determine the direction of F. Let's say B here is into the page. B is into the page. The symbol for into the page is cross, while the notation or symbol for the direction out of the page, from the back to the page to the front, is dot. So this is what I call out of the page, and then this is what I call into the page. If you use Fleming left hand rule to determine the direction of force for my diagram, you can check by using Fleming left hand rule, the direction of force is going upward. Since the direction of force always perpendicular to velocity, you can see from this diagram, or you can see from the position or condition of your fingers. If you put your finger like this, F and B always perpendicular. This is I or V, yeah? This is I or V, the same thing. Since F and B and F and I or V always perpendicular with each other, that means this particle will move in circular motion. So this particle will move in circular motion. Circular motion. That's why if we move into the diagram in this question, since I have a particle that is moved in the magnetic field, there will be a magnetic force acting on it, and then the magnetic force will provide centripetal force, so that this particle will move in circular motion. That's why it will return to the x-axis. Either it will move like this in clockwise direction, or it will move in anti-clockwise direction, depend on the direction of force. So to find the direction of force acting on this particle, we can use Fleming left hand rule. I will write down I here can be thought as V, as the velocity. So if you use Fleming left hand rule, in this case, you just follow this, but you applied it to this diagram. B is out of the page, and then V is going upward. You will get that the direction of force is going to the right. So your thumb, if you follow this condition of your fingers into this diagram, your thumb will going to the right. That means the direction of force is going to the right. But you need to be careful. Why? Because our charge is negative. Fleming left hand rule is used for a positively charged. If we have a negatively charged, the direction of force that we obtain from Fleming left hand rule must be in opposite direction. So, since if you use Fleming left hand rule to this condition, your thumb will going to the right, and since the the charge is negatively charged, that means our force in fact go to the left, opposite with the one that you get from your Fleming left hand rule. Because once again, Fleming left hand rule is used for a positively charged. So since your F is going to the left like this is your F or the magnetic force. That means your object will move in circular motion with the direction of anti-clockwise or counterclockwise. So your charged particle will return to the x-axis on the left side of its origin. That means the value of x1 here should be negative. So I think my answer is either number 1, 2, 3 or 4. It should be negative. Either 1, 2, 3 or 4. This is the correct direction of x. To find the magnitude of x, we can use the formula of circular motion. Since the charged particle is moving in circular motion, as you know, in circular motion we have a centripetal force equals to mv square over r. M is the mass of the object, v is the speed of the object, r is the radius, and then Fc is the centripetal force. In this case, this magnetic force provides centripetal force. So the centripetal force here can be substituted by using this magnetic force. The formula of magnetic force is B times Q times V. F is equals to BQV. So by substitute Fc by using F and then F is equals to BQV, I can say that BQV is equals to mv square over r. We can cancel out the v here, and then as you can see, I get BQ equals to mv over r. That means r is equals to mv over BQ. This is the radius of the circular motion. So x1 is the diameter, not the radius, yeah. R is the radius of the circular motion, but x1 is the diameter of this circle. That means x1 is equals to 2r. This is the magnitude of x1, 2mv over bq. So from this answer, I can say that now my choices is among 1 or 2. 3 and 4 is definitely wrong. 2 VOM over QB. So either 1 or 2. And then if you want to find the T is the time taken from this point into this point. The time taken is T1 or T. To find T, we can find the period of the circular motion first. If you see from this formula, I think BQ, I continue from this part, yeah. I have BQ equals to mv over r. If you remember V is the tangential velocity. I can substitute V by using omega times r. V, which is the tangential speed, is equals to omega times r. Omega, or the angular speed, is equals to 2 pi over periods times r. Omega is 2 pi over period times r. If I substitute V by using omega R, I will get BQ is equals to M omega R over R. As you can see here, I can cancel out the R. That means BQ is equals to M times omega. Omega is 2 pi over T, yeah? Omega is 2 pi over T. From this equation, of course, you can solve for T. 2 pi M over BQ. You have to be careful. This is the period. The definition of the period is the time taken for one complete circle. But in this case, we just want to see half of the circle. Something like this. Since we just focus on half of the circle, that means the time taken here should be divided by 2. Therefore, T1 is equals to half T. Then my final answer is pi M over BQ. So, my final answer for question number 17 is 1. This is the X1 and then this is the T1. This is for question number 17. So you have to know about Fleming left-hand rule and then the formula to calculate the magnitude of the magnetic force, and then a little bit concept for circular motion. Okay, let's move to question number 18. In this question, I have a metal rod R. This is the metal rod R. Is placed on and perpendicular to 2 long parallel metal rails fixed in place in a horizontal plane. So, as you can see here, we have a metal rod. This is the metal rod, and then this is the rail. The rail is perpendicular with this rod, and then we place the rail in horizontal plane. R can slide on the rails without friction, so there is no frictional force acting on our rod while constantly remaining perpendicular to the rails. So R can move or slide to the left or to the right. A uniform magnetic field of magnetic flux density B is applied to a region encompassing the rails. So there is a uniform magnetic field B applied to this whole region in the vertically upward direction. Battery E and switch S are connected to the rails at 1. So we have a battery here and the switch there. The rod is electrically resistant. So this rod has a resistance, but the electrical resistance of the rails is negligible. When S is open, the rod is at rest. When S is closed, the rod begin moving in the direction of blah blah blah. Therefore, the speed of the rod increases and the magnitude of the rod's acceleration is blah blah blah. So, all the information in this question are already indicated in this diagram. We want to find the direction of the rod movement and we want to find the rod's acceleration. As you can see in this diagram, when the switch is closed, current is flowing. The direction of the current flow is from positive terminal of the battery to the negative terminal of the battery. So if I draw in this diagram, the direction of current is flow this way. You have to imagine that the switch is closed, yeah? This is the direction of current. And then you have a magnetic field directed upward like this. Once again, by using Fleming left-hand rule, we can determine the direction of magnetic force. This is your I, and then B is going upward like that. If you use Fleming left-hand rule, the direction of force acting on this rod is going to the left. This is the direction of the magnetic force acting on the rod. So, the rod begin moving in the direction to the left. So my answer is away from the battery. So my final answer for this question is either number 4, 5 or 6. Once again, we use the same concept, yeah, which is Fleming left-hand rule. And then, how about the magnitude of the rod acceleration? Since there is a force, in this case, the magnitude of the magnetic force here is B times L, B times I times L. So we can find the magnitude of the magnetic force in this case by using this equation. B is the magnetic field strength, I is the current, L is the length of the rod, BIL. Since B is constant, B is uniform, yeah? So B do not change. Also I do not change because we do not change the EMF or the battery. And then the resistance is also constant. The rod is electrically resistant, that means the resistance of the rod is do not change. Since E and resistance are both constant, that means I is also constant. And so for L, L is also constant, the length of the rod. So BIL here all have constant value. That means F is also constant. If you remember Newton's law, Newton's second law states that F equals to ma. That force equals to ma. There is only one force acting on this rod, which is F. So I can write down F equals to ma. Since F, which is BIL, is constant and M is also constant, we do not change the rod here. That means the mass of the rod is constant, which is M. They do not tell us the mass. Since F is constant and M is also constant, that means I can conclude that A, which is acceleration, is also constant. That means my final answer is number 5. This is for question number 18. I will proceed to the last question, question number 19. For question number 19, light and electron behave like both particles and waves. Their particle-like properties and wave-like properties are interrelated. So, in this question, we talk about duality of wave particle. So to answer this question, I think you need to know a little bit concept for quantum physics. In quantum physics, wave can behave like particle and particle can behave like wave. We call them duality of particles and wave. By denoting the wavelength of light as lambda, photon energy is proportional to I. Photon energy can be calculated by using the formula E, this is the photon energy, equals to hc over wavelength. H is a Planck constant, and then c is the speed of light. So both h and c are constant. I repeat it once again. H is a Planck constant, which is a constant number, and then c is the speed of light, which is 3 times 10 to the power of 8, which also a constant number. That means the photon energy is directly proportional to 1 over wavelength. So for number 1 here, my answer is 1 over wavelength. So my final answer is either number 5 or number 6. And then, by denoting the wavelength of electron as lambda, this is what I call duality wave particle, yeah. As you can see, electron is a particle, but in this case, electron has wavelength. So particles like electron can be thought as a wave. This is the duality wave particle. By denoting wavelength of electron as lambda, the kinetic energy of electron is proportional to II. As you know, the formula of kinetic energy of an object is half mv squared. To find the wavelength of a particle, we can use the equation that is called de Broglie wavelength. The formula of de Broglie wavelength is lambda equals to h over mv. H is a Planck constant, same with the equation before. H is the Planck constant, m is the mass of the object or the mass of the particle, v is the speed of the particle. M times v here can be thought as momentum, p. If we combine these two equations, I need to substitute the v here. We can find that kinetic energy is proportional to blah 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 in terms of lambda. Okay, I will try to manipulate the equation first. As you can see here, I can write down mv equals to h over lambda, and then from this equation I will times both numerator and denominator with m. Then I will get kinetic energy of an object of electron is equals to half m square v square over m. As you can see here, m square v square is equals to h square over lambda square. mv equals to h over lambda, that means m square v square is equals to h square over lambda square. Then I will get kinetic energy equals to h square over lambda square over m. If you express this into a single fraction, then you will obtain kinetic energy is equals to half h square over m lambda square. Since Planck constant is a constant number and the mass of an electron is also constant, That means the kinetic energy is proportional to the 1 over wavelength square. That means my final answer for this final question is number 6. Okay, that's it for this video. Thank you very much for watching this video till the end. I really hope I can see you guys on my next video. Thank you and bye-bye.